Okay, yeah. Thank you so much. So screen is not shared. The slides are also shared on Zoom. Okay, thank you. Yeah, it's great pleasure to be part of this. So thank the organizers, especially Frank, Herman, Rachel, Erica, and the sponsors for this workshop. So I look forward to a lot of interactions with you throughout the day. And yeah, so the first talk is really a lot of pressure. I think I'll just so most of this I think will be sort of conceptual, philosophical. It's the third attempt to formulate an argument to support intuition I had at the very first time I talked to people about fair predictions using algorithms. So I still not sure whether I have sorted out what I was really thinking. So hopefully you can help me improve the formulation. So it's about the so-called trade-off between accuracy and the fairness of using algorithm, using machine learning models to make predictions or classifications. The plan today is, I have to see. Oh, okay, thank you. So a simple outline. First, I will just describe some background with this issue. And again, for those of the students who attended my guest lecture last month also, apologies for recycling the slides. And after that, so I will present a skeleton of argument. And I try to argue that this so-called trade-off between accuracy and fairness of predictions is insignificant in a sense that I will specify. So I may need to use another term eventually, but for now, let's start with the insignificance of this trade-off. And then I will discuss what I think should be the positive message on this seemingly negative claim that it's insignificant. And in that light, I will, in the end, have time, I very hand-wavingly suggest that conceptually, there's an advantage of using the causal approach to deal with algorithmic fairness rather than the purely statistical one. Okay, so to start, so this issue of algorithmic fairness, in this context, fairness is actually, I think it's about the absence of bias or discrimination of certain sorts. And there are different kinds of biases we worry about in AI applications, and many have been noted in the literature, and for each of them, you may have a corresponding notion of fairness as just absence of that kind of bias. Just give some examples, right? So we may worry about what might be called historical bias. This is the kind of situation where if we just think of purely historical bias, then the data may not be biased in any way in relation to the ground truth or reality. Data can be just very representative and accurately reflect reality. But then in the end, the predictions made by, or the decisions made by some algorithms may still be blatantly biased just because the reality is shaped by some past injustice. So that's one kind of bias. And for example, another kind is representation bias. So here is a sort of more typical, say, sample size issue that databases may contain too few data points for some subpopulations of what we care about. So there's an imbalance between how well a certain population is represented in the database compared to others. And for example, measurement bias is also a very salient issue in classification and prediction tasks. Is that we're really interested in some properties or some variables of interest. They are actually unobserved latent themselves, and they are measured by some observed proxies. So the training of our model is based on observations of those proxies. For example, we may use arrest rate as a proxy for crime rate. What we're really interested in is the crime rate, which is latent or unobserved. Arrest rate is, so they can, to a certain extent, indicate crime rate, but they may also be embodying some systematic bias in some way. And a related one in especially supervised learning in AI is known as label bias. So when we train a supervised, we're training a supervised way, a learning model, then we need to use label data. But the labels, for example, the labels attached to pictures, right? Most of the time are manually done, and the labels may just already reflect some errors, sometimes systematic errors from the people who do the labeling. So you may think it's a kind of a case like this, right? What then you really are observing what some people think of, or what some people would classify certain data points in some categories, even though what we're really interested in is the not directly observed real category of certain cases or data points. So yeah, there are many others we may mention. Now, the technical work in this research is oftentimes formulated as defining precise of fairness for predictions. Sometimes they're also calling this decision making predictions. And most of the time they're just conflated. So yeah, today my main focus is on so-called supervised learning. This paradigm used to be the most useful before the rise of generative AI, but still it's widely used, classification algorithms. So for that, many examples have been noted, right? So I've been using this example in several talks. So this example is very well known. People motivate their work by citing this as at least one of the examples, using this so-called compass system developed in the US by a company, used to be called North Point, and now it's called Equipment. And it's a decision support system used to predict recidivism and to help decide whether some people should be given a parole or should be given a reduction of the sentence time. And so this is a very high profile, very well-known exchange, debate about bias of this system. In 2016, so there is a investigative journalism piece arguing that this system is actually biased against African Americans. And the key observation is that among non-recidivists, Black defendants are more likely to be given high-risk scores than white ones. By the way, how much time I have to talk? 45 minutes. Okay. So please remind me. Okay. But then there's a reply saying that actually campus is fair because it achieves calibration across groups. Among defendants with similar risk scores, African Americans are as likely to reoffend as Caucasians do. Okay, now we'll come back to this in a minute. But first of all, let's first just use a very simple setup for today's purpose. So let's think of a prediction algorithm. It aims to predict the value of a variable y. I call it a random variable. I'm assuming that mathematically we can have a probability space, actually a joint space for all these variables. We consider the target variable y and a number of features or attributes we can use to predict y. So number attributes x, and also we include a protected or sensitive attribute s, which is what we care about fairness about. And S here can be race, gender, right, sexual orientation, those protected groups. And of course, sometimes you can also consider the intersection of them, but today we'll keep it simple. And suppose we just have one of these attributes as the one we care about, a protected attribute. And again, for simplicity, suppose we're just doing binary classification. So y is either 1 or 0. And the prediction system, right, is actually a function of x and s, and we call it a predictor, right? So usually we put a hat on the variable to indicate this is a predictor targeting y. And again, fairness of y hat is in general taken to be absence of some discrimination with respect to the protected attribute s. And depending on how you think of the discrimination, right, you may have different criteria or definitions for what fairness amounts to here. For example, some very most commonly discussed or used fairness criteria in this literature, and very simple ones. For example, maybe the most simple one, right, we can immediately think of is demographic parity. So this one says that there should be an equality parity of the rate of positive outcomes. Suppose y equal to 1. So if you give a prediction of 1, it's a positive outcome. It's one that's desired, and 0 is the undesired one. So this one says the rate of positive outcomes across groups should be equal, or at least roughly equal. Right. So this is one simple criterion we may use. And another one, known as equal opportunity, says that there should be parity across groups in terms of the true positive rate. So in both groups, S1, S2, right, representing the two groups, and given that the true value of y is 1, right? Given that they are not going to recidivate, for example, then there should be an equal chance of the predictor giving a positive prediction. Okay, this is regarded by many as more reasonable than the first one. And then there's another one we may call predictive parity, or some people also call this calibration of what's sometimes called precision of the prediction across groups. So the difference between equal opportunity and predictive parity is the reversal of the role of conditioning here. So in this case, is to say, given in both groups, given that a positive prediction is made, the chance of this prediction being right, should be the same or roughly the same. So this also is related to a very commonly used outcome test, right, in trying to detect discrimination in the practice of law. Now, these three are very commonly discussed, and there's also a very famous impossibility result showing that except in very, very special cases, namely in a case where this protected attribute is independent of y, the target variable. In that case, right, the three can be the three will be consistent. They can be satisfied simultaneously. Except in that case, then you cannot really simultaneously satisfy all of them. And it's also quite easy to prove for those of you who are familiar with, for example, the graphoid axioms for conditional independence. Right? You can easily derive, and in two of them together will entail the independence between S and Y. So I come back to this problem about the inconsistency or generic inconsistency among these criteria. But note that the example we just quickly mentioned, it actually demonstrates the difference between the equal opportunity criterion and the predictive parity criteria. The initial criticism is that the system violates the equal opportunity criteria. But then the reply is actually they satisfy the other criterion, the calibration or predictive parity criterion. Yeah, we'll also see later that this, of course, is not a coincidence. Okay, yeah, for sake of time, maybe I'll skip this. I just say that there are many other criteria, right? There are at least dozens of mathematical criteria explicitly formulated and discussed and used in literature. And a major distinction is between what's called group level and the individual level criteria. It doesn't matter too much for the purpose today, so I'll skip now. If there's questions later, I'll come back. So now let me get to the trade-off. So now a fairly common practice is to enforce in some way a fairness criterion in learning a model from data. And there are many ways of doing this. IBM even has a whole toolkit to help you make your learning to meet a certain fairness criteria. And you may do it actually before learning, the so-called pre-processing, or you may do it during the learning, or you may do it actually after learning to do some post-processing adjustments. So there are various ways of doing that. But the commonality is that in the end, the learned model or the learned predictor is in some way made to satisfy or approximate a certain fairness criteria you impose on the learning. So we'll call this big class of learning methods as fairness constrained learning. Well, again, quite intuitively, and it can also be made theoretically rigorous, is that at least asymptotically, constrained learning can be at best as accurate as unconstrained learning. And suppose unconstrained, we're just trying to minimize some common measure of inaccuracy to minimize error. Then intuitively, the thought is that if you constrain your learning, then you really constrain your search space into a subset of the search space of unconstrained learning. Again, that might be helpful with the limited data, but if you are given sufficient data, asymptotically, the unconstrained learning will at least get what you can get with the constraint in a constrained space. And another theoretical insight is that you should expect that unconstrained learning, when you do it properly, it tends actually to yield a predictor that satisfies calibration. So it's no accident that the campus system we mentioned just now, right? They turn out to roughly satisfy calibration. Because if you just do constrained learning and say if you use the typical empirical risk minimization way of doing it, then it will tend to yield a predictor that will screen off, to use a term philosophers are fond of using, right? Screen off other information in the data set. So in particular, the predictor will screen off the information provided by the protected attribute, right, to the variable y. So it tends to automatically meet this fairness criterion called predictive parity or calibration. So for that reason, right, some authors call this the implicit fairness criterion, the fairness criterion that is compatible with unconstrained learning. But then, as I mentioned, right, those criteria I listed, the three sample ones, they have been shown, right, not to be simultaneously satisfiable, except in very extreme cases. So that means usually if you do unconstrained learning, right, it will be significantly deviant from other fairness criteria, such as demographic parity and equal opportunity. So there's no surprise that we have that campus, the debate about campus. And that also indicates theoretically, right, if you try to impose or enforce the other fairness standard, like demographic parity and equal opportunity, then the accuracy as measured by the standard measures tend to decrease as compared to the unconstrained learning. Now, those are theoretical expect this trade-off, but then empirically, it has been noted and observed in many experiments that once you impose some fairness constraint, sometimes also called fairness intervention, they tend to decrease accuracy, oftentimes by quite significant margin. So there's this trade-off, and has been registered in many papers, but it's also controversial. There are also many attempts in the literature to at least downplay the claim here, usually in the form saying that this trade-off is not inevitable. In many cases, it's not trade-off, right? There is actually, it's even possible to increase accuracy by imposing a fairness constraint. And there are also attempts in the literature arguing that in many cases, the trade-off should not be understood as a trade-off between accuracy and fairness. But I have never seen a paper that's trying to make as strong a claim as I try to make today. I want to conceptually, even if there's the so-called trade-off, the trade-off is never significant as I'm going to define it here, the sense of significance. But my argument, I think, is related to many arguments we see in the literature. I'm still trying to write clearly how they can all be seen as special cases in what I'm going to say. Okay, so let me get to the main stuff. So what my claim is this. So let me first define this. In the end, I may also just formulate this a principle of significance, but I don't want to argue about whether that's a right notion for significance today. So I'll just have a stipulative definition. I hope you at least think this is a meaningful concept. So definition, there is a significant trade-off between A and B, right? Only if both A and B are desirable, and there's a conflict between them. So just say there's a conflict between A and B. Yeah, there's a trade-off between them, but that's not very interesting if clearly one of them is not what we want. So it's significant only when both of them are what we want. And I want to claim that there is no significant trade-off between accuracy and fairness. So here is a skeleton of my argument. So this, again, as I said, is the third time I tried to formulate this argument. Probably after today, I will need to make a fourth try. So yeah, in this skeleton, only two premises. The first premise says that accuracy of the predictor, remember I use y hat, right, to denote the predictor or the model learned from data. Accuracy of this predictor, again, the target is the variable y, right, denoted by y. It's desirable only if y hat does not causally influence y. So the prediction does not somehow influence the true value of y, and also y is really the intended target of the prediction. Right. So I'll explain this more. And the second premise says that if y is the intended target of prediction and y hat does not influence y, so basically if that condition obtains, then I want to claim that fairness of y hat is desirable only if it contributes to the accuracy of the predictor. Already 35 minutes or what? 30 minutes now, okay. Now, if you accept these two premises, then we can conclude that either there is no conflict between accuracy and fairness, or at least one of them is not desirable. So in other words, there's not a significant trade-off as I just defined it. Now, what does the first premise really say? So basically, there are two parts here. You may think of it as two parts, right? The first part says that if y is not the intended target of prediction, then accuracy is not something we want. Because if y is not really what we want to predict. So whether y hat is accurate or not with regard to y does not really matter for us. Now I'm thinking of those cases where this trade-off usually arises and can be explained, which fall into the governance of this premise. For example, measurement bias. Right? So oftentimes, the variable y we're working with and the data we have collected on is not really what we want to predict. It's not the target of interest. So in that case, yeah, you may observe and there may be inevitably sometimes even a trade-off between fairness, some fairness consideration, and the accuracy with regard to the measured variable. But since that measured variable is not really what we want, then the accuracy actually is something that's not really what we want. So it's not desirable. Label bias may also be interpreted at least to be relevant to this premise. So when some trade-off is observed in the situation where they're due to label bias, then you may also argue that in that case, since the labels are biased and the prediction are really trying to predict about the distribution that the labels come from. So it's about, for example, what some particular labelers think about a certain case. That's also different from what we really want to predict. And most relevant, of course, is this historical bias or unfair ground truth. Actually, when I first also mentioned this to my wife, I'm saying, look, there's a trade-off between fairness and accuracy. So sometimes even a perfect predictor, actually by some criterion of fairness, right? Even a perfect predictor may turn out to be very unfair. Well, the initial reaction I got from her is, that's obvious because the reality, the ground truth, right? He said, reality is biased itself. So the ground truth is biased, and we have this biased model or predictor. And if you want to impose a fairness constraint, then the result will not reflect reality as well as the unconstrained learning. So very intuitive and obvious. But again, in that case, I would say, yeah, what we really want to predict in that case is what the world would be like if some historical bias were absent. So we do not really care about accuracy with regard to this unfair reality. At least under some interpretation, we can do that. So in that case, again, there's a trade-off, but the trade-off is insignificant because in that case, clearly we don't want that accuracy. And well, the second part may be a little bit more harder to, a little bit harder to explain. But basically, I'm trying to claim that if y hat causally influences y, so I will call this a case of active prediction. Right? So the prediction actually influence how things will come out. Of course, think of self-fulfilling prophecy or self-defeating prophecy, right? That kind of situation. Then in that case, again, this is all very rough for the moment. I would be happy to discuss this more during Q&A. What matters is how to achieve desired values of y through y hat rather than accuracy. So intuitively, if you achieve a desired value of y by making a self-fulfilling prophecy versus you actually realize a desired value of y by making a self-defeating prophecy. So one is accurate in some sense, it matches the other is very inaccurate, but there's really no difference between them if in the end it's the desired value to be realized. Now I mentioned, I include this part, I usually didn't have this part in my first formulation because I thought these days there's also very interesting work on so-called dynamic fairness. There are many also kinds of work in this broad literature, under this broad umbrella called dynamic fairness. But one line of research I'm more familiar with is actually trying to use fairness interventions, right? Not to let a certain predictor satisfy some criteria, but rather the goal is to realize in the end, in the long term, a data set or a distribution that actually satisfies a fair criterion. So it's not to let a predictor satisfy something, but let the state of affairs satisfy fairness. So in that case, of course, it's using fairness interventions, if any, to try to achieve, to realize some state affairs. Well, again, in that case, if you just measure accuracy, then there may be a trade-off, but that kind of static accuracy is not what we care about, right? What we care about is the long-term realization of something. And also, more extremely, I'm thinking of, I can even accommodate, right, just decision-making, a prediction as practical decision. So imagine I'm just building a model based on what I observed past decisions have been, and then trying to predict the decisions. But then, as a matter of fact, this prediction is just, right, making some decision to be true. In that case, again, accuracy is not the issue, right? It's more about whether the distinction you bring it about, right, will be desirable and some other kinds. In those cases, fairness should come in. Okay, this is very quick, but I'll just leave it here and maybe we'll come back later. So that's the first comment saying that, that's the first premise saying that only under some situations we care about accuracy. And then the second premise says that in those situations we care about accuracy, then we may also care about fairness. But I think in those cases, fairness is desirable only to the extent that it serves epistemic purpose rather than some ethical purpose. So it's 5 minutes or 10 minutes left. Okay, good, thank you. So why do I think this is the case? Now, this is really my very first initial intuition. So call a predictor passive if it does not influence its target. So again, if y hat influences y, I call that an active prediction. But if it doesn't, then it's passive. Now, premise 2 is based on, I think, a truth norm for passive predictions. A passive predictor, as a predictor, it aims at true values of its intended target variable. So that's the sole aim of making a passive prediction. There is an independent ground truth, and if you say that's really what you care about, that's the intended target variable for prediction, then all it matters for this prediction is to get it right or get the true value of this intended target variable. Now, but that doesn't say that we just totally ignore the fairness, at least as they are proposed in the literature, because oftentimes they may actually serve a purpose. They serve to improve predictive accuracy. So there's very interesting work, for example, several years ago, published in Neurips by Wick and others, right? They show quite convincingly in some simple setup, right? Because there's label bias, there's selection bias. Look, these are all epistemic biases. And if you use some clever way to impose a fairness constraint, it actually helps to increase the accuracy. But it's accuracy regarding the real target, right? So there's an apparent target in those cases, but which is not what we really want. So there is a trade-off there between the surrogate accuracy with regard to those apparent observed surrogates. So if you look at that accuracy, it's a trade-off between that accuracy and fairness interventions or constraints. But if you look at the real accuracy, right, regarding what we really want to predict, then there's no conflict. In fact, right, imposed fairness intervention may help you to recover what you really want to predict to help correct these biases. Or something, I'm still trying to work out example. This is really what I want to claim, right? It will help with sometimes with counterfactual inference when y is about whether property would have been instantiated if certain historical biases have been absent. So in those historical bias case, either you are really just concerned with what happens to be the case, no matter how fair or unfair it is. Then in that case, yeah, you care about accuracy, then you should ignore fairness. because that's all you care about, just how things are as it happens. But when we care about fairness, I think it's because we really want to predict what the value would have been if the biases had been absent. Well, in those cases, actually, doing some fairness interventions may help with this epistemic goal. So the moral is this: it's not to say we should just forget about fairness in making predictions. Rather, we should be aware that there may be many epistemic gaps or biases, and fairness considerations, when they are applicable, they actually do not compromise. At least they should actually serve epistemic goals. So that should help us to decide which fairness consideration is the right one in a certain context. Specifically, they can potentially be leveraged to correct a mismatch between the real target of prediction and the observed surrogate. So with that in mind, and then I want to say 5 minutes, is that okay? Okay. In fact, it should be more conceptualized along the causal approach. So in the literature, initially, it's all about those definitions in terms of associations or independence, probabilistic independence of some sort. We can call them associative or statistical fairness criteria. But then later, many people who work on causal models in AI, right, they start to also introduce criteria that are explicitly formulated in causal terms. So you may call those causal fairness criteria. So the sample ones I mentioned earlier, right, they are all associative. They didn't mention anything about what causes what. But for many purposes, right, it may be more relevant to consider the protected attribute causally influence the prediction, right, rather than just provides information about certain variable. Now, again, in the literature, there are many arguments for why the causal approach is the right one, or more important, more relevant in some situations, like if you want to actually conceptualize procedural justice rather than just substantive justice. Sorry, happens here. Or maybe this telling me I should stop. Oh, okay. Oh, okay, thank you. And for example, if you want to differentiate between disparate treatment versus disparate impact, and if you want to distinguish between direct versus indirect discrimination, so all those things have been noted in the literature. And there are some, so here I just give some examples. I think I can skip that, but basically it says, right, it's fair if the protected attribute has no or negligible net effect on the prediction in some sense. So you can talk about has no net effect or has no direct effect, or the most sophisticatedly, you can talk about has no effect along some problematic causal pathways. So very, I mean, just a short while ago, right, a very comprehensive survey, several hundred pages, right? It's published by Jago Plako and Elias Barabaum. It's really a fantastic reference to this line research. But I'll just stop by saying that, in fact, if you buy the argument I just gave, then the positive message about fairness is just that fairness, if they really should play a role in making predictions, they should actually help to serve the epistemic goal of correcting some epistemic biases. And it's supposed to help predict what the value of Y would be if certain kinds of bias were absent. So it's really a counterfactual question, and we need causal information to answer that. Or in the case of active prediction, right, again, as I mentioned, dynamic fairness is supposed to help produce fair states of affairs in the long term. So once again, it's the causal information that's needed here. A merely associative information may not be enough. Okay, let me conclude. So this is very, it's just a suggestion. If I'm then when there is a apparent trade-off between fairness and accuracy in algorithmic predictions, either the fairness or the accuracy is not really what we want. And when it comes to passive algorithmic predictions, fairness analysis is valuable only insofar as it helps to improve accuracy. So there's no significant trade-off. For this purpose, I think the causal approach is probably more relevant than the associative approach. But of course, in practice, as always, it's much harder to implement than the simple associative criteria. Okay, thank you for your attention.